Hi, I'm Anna Spencer. Today we're going to talk about concrete. And today is a very important day. And it's the first in a series of what will be 16 or 20 hour-long conversations that are being held in conjunction with the Canadian Pugwash Group. And the thing is that pugwashers have been interested in nuclear weapons and weapons of mass destruction since the very beginning, but not as much as we should be about some of the other global threats to humankind, such as global warming. But we're going to pull up our socks and get busy and try to rectify that omission now, because we have a project where we're going to be having conversations over a period of for the next 4 months about 4 different possible interventions that might be useful in reducing the threats of or the amount of climate change. So one of them has to do with the rapid adoption of low carbon concrete, or what I would love to hope for, carbon negative concrete, which then would not only stop being the source of something like 8% of the world's carbon emissions these days, and then become a real a sink for almost the same amount of carbon, because concrete is a very heavily used material. And if we actually get to the point of using and being able to produce adequate amounts of carbon negative concrete, we'll be able to do a great deal to reduce the threat of global warming. So I have some experts here on carbon, and some people who are also knowledgeable, mostly physicists and other scientists who are members of the Pugwash community, and we will have a conversation about the potential for adopting low carbon concrete, or as quickly as possible, carbon negative concrete. My experts today are Professor Doug Hooton of the University of Toronto.
Good morning, everyone, or afternoon, I guess.
In London, we have Chris Cheeseman, who is at the Imperial College.
Yes, good afternoon, everybody. It's actually 4:30 in the afternoon here. And I work in the Civil and Environmental Engineering Department at Imperial College, where I'm head of the materials section. And our materials section is focused on advanced infrastructure materials. Yeah.
Thank you. And in Vancouver is Michael Barnard.
Advisory board, electric aviation startups, advisory board, redox flow batteries, the Future is Electric think tank that I run. A couple of other things emerging, so watch this space.
In Berkeley, California, Neil Hoot, who is a professor at Queen's University normally, but he's on sabbatical in Berkeley.
I'm a professor in civil engineering at Queen's, and as indicated I learned about concrete materials from Doug Hooton, so he knows way more than I, but I'll try and contribute on the structural and engineering end of things.
Mm-hmm. Okay, very good. And we have some physicists. We have Alan Slavin in Peterborough, Ontario at Trent University, retired physicist. Peter Meinke as also a physicist. I guess your last job was the president of the University of PEI. And Adele Buckley, who is another retired physicist here in Toronto.
I've been following concrete off and on for a little while, and so I'm really interested in what is said today.
Very good. And in Vienna, Austria is Tariq Rauf.
Hello, everyone. Glad to be here.
Good. Who's an expert on nuclear matters. And he is going to be the co-chair of this section of the work that Pugwash is undertaking to investigate concrete. So he and Robin Collins. Okay, now let's get down to business. I'm particularly keen to start with Doug Hooton because I'm so thrilled to have been able to catch you. let's say you and I had a conversation yesterday, and basically what I took away from that was that our project is really not going to even be necessary because concrete producers are already mandated by the Canadian government to start producing low carbon concrete, and that the government is going to purchase low carbon concrete. And so our work is already done. Is that fair? Let's
that's an oversimplification, I guess. But we're on the road, I guess is the point. And maybe I'll just say a few more words about my background because I just said hello earlier. I'm actually a professor emeritus now. I retired during COVID. But I chair the Canadian Concrete Committee, the CSA committee. I chair the ASTM Cement Committee in the US, and I chair the several committees at the American Concrete Institute. And I do consulting on sustainability as well as that. I've had a research chair, an NSERC research chair for the last 12 years on sustainability of concrete. So I've been working with the industry and with the government to try and improve things along. I'm not alone in that regard. But I guess, yeah, the government just came out with a report on November the 9th, which you can download, on improving sustainability right across the board, not just the cement and concrete industry, but all the supply industry, the whole environmental reduction. And their target is to reduce 40% of emissions by 2030, which is a pretty aggressive target. And then the ultimate goal everybody has is the 2050 net carbon neutrality. And by net means there will be emissions, but they'll be balanced out by other things. But if you want to know a bit more concrete, I've got about half a dozen PowerPoint slides if you want to take the time to walk through it, just to introduce the topic. Sure.
Okay. You think that it's very aggressive, 40% by 2030 and net zero by 2050. I think that's piker. I think we can do a lot better than that, but go ahead.
No, I think you underestimate the ability of things to change that quickly. But I understand why you'd think that. But just to introduce, this is a data from the University of Bath in the UK, and Dr. Cheeseman, I'm sure, is aware of it, showing embodied CO2 and embodied energy on the x-axis of all the building materials that are used. And what you see there is concrete is the lowest embodied energy and lowest embodied CO2 of all the building materials that are used today. And you can see that steel and plastics are way up at the other end. Cement, which is the largest producer of the CO2 in the concrete industry, is a component of concrete, is only one small component, about 10 to 12% of the volume of concrete. So the concrete is lower than the cement because cement is an ingredient. It's not a final product. Well, you can see even with biomass neutral, timber is higher in spite of the timber industry's government-funded efforts to show they're not. So why is this important? Even though it's the lowest embodied energy, concrete's the most widely used material on Earth. So we're looking at 20 billion tons a year. And so it has a large impact on energy and CO2 globally. But in the parens there on the right, you'll see, according to the EPA, it's only less than 1.25% of US CO2 emissions, even though the global part is 7%. And it's about 1.4% of Canadian emissions. So we're well below the average. And the reason for that is 50% of all the materials produced for construction are concrete. But in spite of that, the CO2 emissions from the concrete industry are about the same as the steel industry and less than the timber industry, even though the volumes are much lower with those materials. So concrete gets a bad rap because everybody knows that, well, people are aware of the fact that CO2 is emitted in the production of cement that goes into concrete. So we need to still make an improvement. That doesn't prevent us from making an improvement. And so where does this come from? We get about 650 to 900 kilograms of CO2 per ton of cement that's produced, cement being the one component of concrete. And about 60% of that comes from decomposition of limestone calcium carbonate. When you heat it up, the CO2 comes off and you end up with CaO, which is then combined with the other ingredients in cement. So that's a chemical decomposition that they can't avoid. The rest is coming from fuel. And so the industry, though, is very thermodynamically efficient. They're looking at about 80% thermodynamic efficiency, and this is actually out of date. It's actually up to about closer to 85 now, which is pushing the limit. And they're using more and more waste fuels. In Europe, waste fuels, as opposed to like coal, powdered coal, or oil or gas, are substituting much more of fuel than we do here. We have restrictions that restrict the amount of wastes that are allowed to be used as fuel here in Canada. So there's the chemical reaction. Calcium carbonate goes to calcium oxide and CO2. That happens at about 800 degrees Celsius. And cement, to make the cement, has to go up to about 1450 Celsius. So it's well beyond that limit. So that the primary emissions are coming from that chemical reaction of limestone being decomposed. So why is the world 7% and we're so low? The industrial countries are pretty well developed, and they're down there at the bottom. Where you see the big plays here with CO2 emissions is China and India and other developing countries, South Asia and Africa, that are coming on and will continue to grow. China is probably peaked now, but China produces more cement in a year than the US did in 100 years. It's just a huge scale. So what we do here is small relative to what they do, but we still need to deal with it. But as I said, cement is only one ingredient of concrete. If you look at the embodied CO2 and embodied energy of concrete, the dark blue there is the percent that's coming from the cement, even though it's only about 10 or 12% of the volume. It's responsible for the vast majority of the CO2 and energy because it's the energy efficient. The rest is stone and sand and water and a small amount of chemicals, but it's largely coming from the cement component of concrete. But this is US data, it just came out earlier this year. And the industry has developed environmental product declarations, product specific and location specific. There's over 60,000 environmental product declarations for concrete out there now. And they've just released some new ones for Canada, which are regional. And these are third-party verified EPDs. And they've reduced in the last 7 years, say 8 years, they've reduced their CO2 emission, global warming potential, which is largely due to CO2, almost exclusively, by about 20%. And they're adopting new changes now. Portland limestone cement, I say at the bottom there, is coming on strongly in the US for the last 18 months. And so we'll expect to see another reduction by next year. And they think they're going to make this 50% reduction by 2030 in what they started out with in 2014. Now, they were off to a good start. Whether they can continue that's another story. Hopefully they will. But people are paying attention to it because the large players like Amazon, Meta, all these big players are asking for sustainable solutions when they build things, these large data centers and supply centers. So the customers are asking. The US government, the GSA, has put in limits now in the US.
Doug, if I may ask a question, please.
Sure, absolutely.
What is an SCM?
Oh, I'm sorry. Cement replacement materials, supplementary cementitious materials. So we use largely industrial byproducts, fly ash from the coal power industry, which is going the way of the dodo bird at the end of this year. As a replacement, you can replace 20 or 30% of the Portland cement with that. It has cementitious properties. Blast furnace slag from the steel industry, you can replace 25 to 50% of the cement with that. We can also use natural pozzolans the way the Romans did, volcanic ash and materials, although we don't have a lot of volcanoes here. There are clays that we can heat treat at a low temperature and use them, and there's some out west. So there's some of these other materials coming on that can replace the cement. And so supplementary cementitious materials are being used more and more to replace the Portland cement, which is what I showed in that big kiln earlier.
Yeah, thank you very much for the definition. Just a point of clarity for everybody involved. The blast furnaces will be diminished. The United States is already at 70% use of electric steel mini mills, and that's going to increase as steel decarbonizes. And similarly, Doug's already mentioned that coal is going to go away, so that cementitious material is also going to diminish as a source. And Thankfully, we don't have a lot of active volcanoes in Canada, although I did have a view of one in, Washington State. The point there is that this is a temporary solution to the problem. We do have a lot of those materials from coal and steel manufacturing, but it's not a perfect solution yet.
No. One thing we've done, though, I just involved changing the Canadian standards last year that now allow you to mine the backfills of fly ash, the landfills that exist. And there's in the US alone, there's almost 2 billion tons of landfilled fly ash. And that's enough to supply the ash for the concrete industry for the next 50 to 100 years, depending on the rates they use it at. So they have to process it, but it's basically a mining operation and getting rid of the landfill at the same time. So there is an opportunity. We're already doing it in Alberta. There's 3 plants doing it in Alberta already, because there's at the end of this year, there'll be no coal generation in Alberta. And I think the only ones left then will be in Nova Scotia. The cement industry, this is the Portland Cement Association in the US, but this is happening in Canada, it's happening globally, are doing roadmaps to carbon neutrality. And that's a big thing that's been coming on for several years. And the clinker is the raw material made in the kiln. The cement is the final binder, which has more than things than clinker in it. And that's the space I work in concrete, which is the product people use. But there's also things you can do to reduce energy in construction. And eventually, concrete is a carbon sink. Oh, that's a long way off. It actually sequesters carbon over time, but that's a small issue, a small item.
Doug,
Yep.
Another definitional request, please.
Sure.
PLC, and you've mentioned waste fuels twice now without defining what a waste fuel is. So if you could share that, please.
Sure. Well, Portland limestone cement is, we take the raw limestone and not put it through the kiln, grind it up, intergrind it with the cement clinker that's made in the kiln, and use it to replace about 15% of the cement. And it turns out we can do that without any negative effect on strength.
Oh.
And so we've allowed that in Canada since 2008. It's only really been picked up in the last 5 years here. So almost all concrete cement in Canada now has 15% limestone or up to, which has reduced the carbon footprint of cement by about that amount, that direct replacement. In the US, it's been allowed since 2012, but it's only in the last 18 months where people have gotten past it and they're actually using it. There's a lot of barriers to the use of any change. It should be plug and play. In other words, you should be able to replace Portland cement with Portland limestone cement with no influence, but people fight it up and down. And I've been going through battles the last month with various not organizations, but private companies who are claiming the sky is falling, Chicken Little. And something that makes such a small change in the properties of concrete is just, it's not the first time this has happened with the change in the industry, but it always surprises me. So your second question was about waste fuels. It turns out that the cement kiln, because it operates at very high temperatures and has a long residency, 20 to 30 seconds at those high temperatures, it can destroy almost anything. You can put tires in there. A lot of plants do that. You can put wood waste in there. You can put petrochemical waste in there. Carpets, all kinds of crazy things. In Europe, some of the plants are running at 80% waste fuels now. But in Canada, I think the average is about 10 to 15%, because every province has their own regulations of what's allowed, not allowed. And so it's changing though. So as opposed to burning, most of them burn powdered coal now, although out west they're switching to gas in Alberta because they have it. So that's what I mean by waste fuels. But this road, if you want to interested in the roadmap, just go to cement.org and you can download this for free. I can supply that. So what I work on is what we can do to get down that 40% by 2030. We can do a whole bunch of things in concrete. One would think that the sand and stone would be optimized now, but they're not in a lot of instances. We can reduce another 5 to 15% of the required cement in concrete and improve the concrete quality by optimizing the cheapest thing in the concrete, which is the sand and stone, the gradations. But it's not being done largely due to capital investment in the concrete plants, having the extra bins to do that. And again, Portland limestone cement, about 10% reduction. If we replace cement with supplementary materials, which could be waste industrial material byproducts or natural pozzolans, we can reduce the CO2 almost in proportion to the cement replacement. So we can easily get to 40% with these things that are allowed now, and they're all allowed in the standards. Sorry, Adam, you had your hand up.
Yes, Adam.
Yes, thank you. I was just wondering if increasing the amount of limestone within the formula results in any impact on its longevity, specifically with erosion and the impact of acid rain and other environmental factors. Because we know limestone as a building material tends to erode if it's exposed to acid rain.
Well, cement is also a lime-based material, and it can be attacked by acids. So concrete generally can be attacked by acids, but the amount we're talking about is very small here. And we actually designed the standards because I was involved with designing the US and Canadian standards for Portland limestone cement to make them identical in terms of when they turn from a liquid to a solid, the setting time, and the early strength development, which affects construction schedules, which is huge for the contractors. So we designed them to be equal performance from a physical perspective. And in terms of longevity, they're just as durable. I've been working on that for the last 12 years on durability of limestone cements and concrete to all the different things that can attack concrete. And there's no negative impact of using them.
Thank you.
Okay.
So we can do all these things, but there's barriers. And I'll just go down to the last 3 bullet points here.
Mhm.
We've already allowed all these things I talked about in the last slide in the national standards, CSA and ASTM, which are the national standards. But every state, every city, and there's lots of private specifiers, there's over 2,000 specifications in the US alone for concrete. So people don't just adopt the national standards, they got their own, and they often put prescriptive limits in. A lot of specs in the US and in Canada have minimum cement content. So even if you could make the concrete with less cement, they're not allowed because these people have these old specs that probably go back 50 or 60 years, and they no longer have the expertise to understand how to change them. But they're not willing to change them. So this specifiers cause a problem. But there's problems all the way along risk because there's legal liability for putting up a building and it doesn't perform in terms of public safety. But there's also financial liability if things don't come up. And so the contractors see a risk, the concrete suppliers see a risk, even the finishers on the job see risk. How does it affect them when these changes occur? And there will be subtle changes. And that's where I've been working on. I've been trying to work with some of the NGOs through Breakthrough Energy to help deal with some of those issues. We're hoping to develop some educational programs because we need to get past those barriers to accelerate the adoption of these things. And lastly, after 2030, the prime thing to get down to net neutrality will be carbon capture and storage, because the concrete industry does produce CO2 because of the kiln operation. And that will likely raise the price of cement by a factor of 3 or 4 times. And then you've got to do something with that captured carbon. If you live near the sea, like in Norway, they're putting up a plant, they're going to put it under the old oil fields. There's 2 actually pilot plants in Canada, one in Edmonton and one in Vancouver, where they're doing carbon capture projects. And so the industry is already trying to work on this, but they're having to develop the technology. It's estimated you need the same sort of, if we put it at every cement plant, you'd have to have CO2, well, not just cement plants, but all the industries. You'd have to have CO2 pipelines, just like gas pipelines, going across country to take it to somewhere where it could be stored and sequestered. So there's a bunch of issues there, and that's going to take time because you can't turn that on.
Yeah. I think that you're understating the issues with carbon capture and sequestration. Something I've assessed every substantive carbon capture and sequestration program globally, and mostly it's a shell game for the fossil fuel industry to perpetuate, their life, and it's not something that can effectively scale in mechanical carbon capture and sequestration, which is a significant problem for a lot of the net zero assertions. I do have one question for you, Doug, before we move off of this, which is, one of the major wedges in reduction of CO2 emissions globally is moving to electrification of everything that's possible.
Right.
I've heard mixed. Certainly we can produce very high quality industrial heat with electric arc furnaces. We use them in electric steel mini mills. We use them in aluminum smelters. The question for you is how much electrification of a cement plant is actually possible in terms of provision of heat? Because I know there's some chemical aspects, especially in the clinker drum, related to the jet of flame that has something to do with it. And I don't know the details of that.
I won't claim to be an expert in all these things, but the industry is looking at electric. I'm involved with the Global Cement and Concrete Consortium's Innovandi research project, and they're funding projects on electrification and of parts of the industry. They can probably do the lower end, the calcination part of the kiln, which is just getting rid of the CO2 in the limestone, which takes place at 800 or 900 degrees. They think they can get that part electrified.
Mm-hmm.
Well, it's possible to do that, but I don't think it's possible to get all the way at this point in time. They're looking at electric fleets of vehicles and other, electric generate. A number of plants have developed cogeneration plants to use the waste heat to develop electricity. But these things they're doing them, but it's going to take some time. And I'm not sure how widely adopted.
A question or a comment, Tariq? Tariq?
Yes, thank you. Yes, thank you. So I was looking at an article in Concrete Quarterly, and they're talking about a British standard called BS 8500 based on Portland cement, and they refer to it as CEMI. And this article claims that a concrete mix of CEMI 3B has more strength in the concrete for load-bearing structures than normal concrete, which apparently reaches its full strength at 28 days. And with this CEMI 3B, it can gain a further 40% by 56 days. So could you, for a non-specialist, describe what might be the advantage and what are the concerns about low carbon concrete for heavy load-bearing structures? Thank you.
Sure. Well, CEM 3B has 65% blast furnace slag replacing cement. It's the predominant cement used in the Netherlands, for example. It's a very good material. And again, it reduces the clinker component, but subject to what Michael mentioned, the blast furnace, availability of blast furnace slag is going to diminish with time as they go to direct reduction electric arc furnaces to reduce the steel industry's CO2. So right now, that's widely used in Netherlands. It's funny, though, that the same company that makes CEM 3B in the Netherlands does not promote it in the other countries in Europe where they sell cement. There's like national things. CEM 1 is just the CEM 1, which is just Portland cement in the European standard. So BS 3500 is the same as the EN 197 national standard or European standard. So one's Portland cement and one's a 65% slag. They actually have 37 types of cement in the EN standard now with various amounts of filler. Some of them are limestone fillers. Some of them have fly ash replacements. Some have slag replacements. Some of them have natural pozzolan replacements and different proportions. So they have 37 types of cement. Not that those are available everywhere. Typically, any country has 2 or 3 within the European Union.
So could you comment about the strength business for high load-bearing structures? This 28-day versus 56-day business, whatever that means?
Sure. Well, some of these cements, especially the ones that have a lot of replacements with things like slag or fly ash, develop their early strengths more slowly, but they develop better long-term strengths. So if you can wait like beyond 28 days, they do better things. And our Canadian standard actually reflects that. We have set our specs for the high-strength concretes at 56 or 91 days because we know that happens. But then from a construction scheduling point of view, if you're a developer, especially in high rise, that means it's going to take you a lot longer to put up a building. And construction schedules dominate the vertical construction industry. For a lot of concrete, it wouldn't matter, residential, that sort of thing. So one of the things with the limiting CO2, and I've discussed this with the people in California about legislation, is you've got to set a target for the whole project, because you may need small amounts of concrete to develop the strength quickly to speed the schedule, but you can make up for it by using lower CO2 concretes than the rest of the project. So your total project meets a target. But if you limit them to every piece of concrete, every cubic yard or meter has to meet a target, then you're going to have a severe impact on the industry and there'll be severe pushback. So the trick is that these concretes develop their properties at different rates. And so you've got to allow the flexibility. So when something like a column in a building, which often restricts when they can move up, and they use small amounts, though. Columns take a small amount of concrete. You allow them to use a fast concrete there, but on floor slabs, you could use something that moves more slowly, or in foundations and those sorts of things.
Thank you.
So another piece of context for this discussion, which is important, is that the ratio of embodied carbon to heating and other carbon is changing as we electrify. So as we move to heat pumps and away from natural gas furnaces and oil furnaces, which are fairly prevalent in Canada, and as the grid electricity decarbonizes, the residential and commercial heat provision and air conditioning provision decarbonizes radically. And so for new buildings, one of the key things is to reduce as much as possible the embodied carbon, because that becomes a dominant component in the carbon footprint in the space. In Vancouver, of course, where I live, we've now moved to ban the use of natural gas in new buildings, and in major retrofits, they have to go away. In the condo building I'm in with 300 units, we're looking at, probably in the next 5-7 years, as the gas boiler ages out, we're probably going to replace it with a heat pump system for, commercial buildings, which is completely fit for purpose. And so, that's one of the reasons that I attend to concrete. While it's, I call it the gray glue that holds our society together. But it is a carbon problem that is going to become a greater percentage of the carbon problem for new infrastructure.
However, on the other side of that, concrete is a good thermal insulator in terms of it acts as a heat sink too. You can actually reduce your heating and air conditioning costs if the buildings are designed to take advantage of that. So you actually
that's a big if.
That. Well, no, it's been shot. There's a lot of data out there. We've instrumented buildings.
Oh, no, I don't disagree with you about the ability for it to done. The big if is if the building is designed to do that.
Right. And that's where architects should be spending some of their time. I'm not sure.
Once again, though, if heating is electric and the grid electricity is decarbonized, then the value of the thermal load in the concrete is diminished substantially. It may be the way I describe it is that building efficiency becomes an economic virtue, not a climate virtue. And so as we think about that, as we move through heat pumps and decarbonizing electricity, then the rest of the question, like for example, fixing building envelopes so that they're less leaky, putting in insulation, those become economic value propositions as opposed to climate solution value propositions. The balance is changing over time in space.
Sure, but that right now, where the biggest plays are in China, India, and developing countries, China opens a new coal plant almost every week. At least they were prior to the pandemic.
I would like to point out that China has builds more wind and solar every year than the rest of the world combined, has built 40,000 kilometers of high-speed electrified grid-tied rail, is building more grid storage, has turned on more hydroelectric, et cetera, et cetera, et cetera. The coal problem is going to go away in China, and they're well ahead of targets. Anybody who chooses to bring up China as the reason we should not be better here is going to get an argument. So please, let's stick to the topic.
No, but I'm just saying right now, I've been to China many times and you cut the fog with the smog from the coal plants. I walked right up to a coal plant. I couldn't even see it. But
and
I understand what you're saying. It doesn't prevent us from doing anything.
China has cleaned up its air substantially in the past decade. It has planted more trees, planted over 4 billion trees in an area larger than the size of France. It's improving those things. It has 500,000 electrified buses on its roads. Once again, stick to cement in Canada, please.
Okay.
I will argue
Yeah.
quite a bit if people choose to bash China as a reason not for us not to be better.
No, I'm not saying we shouldn't do anything. I'm just saying you got to be careful what you believe when it comes out of China. There's over 1,000 cement kilns in China that have 1800s technology. And if you ask anybody about it, they will deny they exist. And they're totally inefficient. But it's just like the coal mines, they say don't exist anymore because they shut them down. But then you hear about coal disasters where they're still operating. You got to be very careful about what you believe coming out of China. They're doing. I agree with what you're saying. I've been on their high-speed rail. I see what they're doing. They're big hydroelectric plants, but they're still doing a lot of other things. It's a huge country with a huge population.
So a related question is in a lot of developing countries, they use brick kilns. They use baked bricks. So the concrete
Yes.
is just the binder, but most of the construction is bricks, like in South
Yeah.
Asia and so on. And most of these brick kilns are also 18th century, if not older technology, using coal of various types, also slave labor conditions. So what's the solution for these countries where for them, these baked bricks are cheaper than concrete if one is making a house or a developer?
Yeah, well, there's a whole bunch of issues there. One of them is the environment they're building in. They never see freezing, which is a huge issue. They have a lot of clay resources there. This right around the equator, about 20 or 30 degrees either side of the equator, there's huge kiln and clay deposits, which can be utilized as a cementitious material or used as a building material, like you said, like adobe type brick materials, and they do use it. So the other thing is that most of the cement that's used in developing countries is not coming out of a ready-mix truck. It arrives on a site in bags. Some of it's mixed by hand, some of it's mixed in small mixers. And typically those sorts of concretes use about 4 or 5 times as much cement as you would with a sophisticated ready-mix plant. So they're totally inefficient in terms of how they use the cement. But that's what they have. A lot of the times it's due to the transportation network, and the industry hasn't been developed to have those things. And maybe that'll change with time.
We have had
So from-
2 talk shows already, mostly featuring Blue Planet concrete. And one of them was with Brent Constance, the founder and inventor of the technology, which is not only low carbon, but extremely carbon negative. And the second one was with Chris Cheeseman here, who can probably recount what we talked about the other day with Peter Fikowski, who made a trip over to the Blue Planet production site and gave us some photos of what they're doing there. Now, if you can speak to the question of whether or not it is really true that carbon negative concrete is far, far in the future, or whether, as I understand it, it's right here and now. When I talked to Brent Constance several months ago, it may have been about a year ago, he said, I believe that they're building 60 Blue Planet plants in China.
Okay.
And God knows what they're doing now, because he's obviously a ball of fire trying to promote the thing. Chris, can you speak to this whole question of whether or not carbon negative concrete is actually in the wings waiting to make its appearance?
Yeah, well, I'd like to start by saying that I agree with everything that Doug said. Actually, I mean, that was a great introduction to the current situation where we are. I think so the Western world is moving definitely in the right, or the developed world is moving in the right direction. But I think Michael was saying to keep the focus on Canada. But in terms of course, global warming is a global issue, and we saw from one of the graphs that Doug showed that cement production is increasing in many parts of the world where the same sort of technologies, they could be used, but they're just they're behind, and then they're unlikely to instigate those things in the near time. So I wanted to make that point to start with. Now, the Blue Planet technology is very interesting for sure. So this is where these guys are making carbon negative aggregate. So that's quite a revelation to me, actually. I haven't seen the plant, but I was in discussion with the people who were involved in it. And it does seem, because if you're going to make that huge part of concrete, which is the biggest part of concrete, which is the aggregate carbon negative, then that changes the balance. So that's very interesting. I think the points on the problems with future supply of coal-fired power stations, fly ash, and blast furnace slag are very relevant indeed. So our research at Imperial College is looking to develop some other types of supplementary cementitious materials, which are themselves also carbon negative. Right. So I think this is a really exciting area. Yeah, and if you combine carbon negative aggregate from the Blue Sky, Blue Planet, sorry, not Blue Sky, Blue Planet, and you combine it with some of the very interesting, the carbon negative supplementary cementitious materials which could come along. That's the SCM that Doug defined. Then you could actually move to a situation where you could see quite carbon negative concrete, which is beyond what we were thinking about a few years ago, really. But it's very exciting, I think. Of course, the problem is, as I said earlier, isn't the USA, Canada, or Europe. It is how you get this technology into Southeast Asia, because that's where the big growth in concrete use and therefore carbon emissions is. Meta, I'm not sure that's answered your questions, but those are my comments.
Thank you. Also, Michael Barnard, you were the person who drew my attention to Blue Planet in the first place. And so you may be more familiar than most people with it. Do you have any comments about that?
The comment I have is that I think you have a false memory. I don't think I did bring Blue Planet to your attention. I did. I certainly talked about cement with you a year or two ago as a significant issue that we had to deal with. I talked about the efficiency conundrum that we're, the shift in balance that we're coming into. But I don't believe I mentioned Blue Planet. That said, I did look at Blue Planet, and I do spend a fair amount of time looking at the chemistry related to carbonates and stuff. Contextually, Agora Energy Technologies is an electrochemistry solution which uses gaseous CO2 and bromine in a redox flow reaction to create formate and can actually create carbonates and bicarbonates as an additional process there. So I've looked at those things. I've looked at the CO2 reactions out of limestone kilns as well. It's like one of those fundamental things that goes on. And so as I look at the Blue Planet technology, I looked through I looked as much as possible at the chemistry. There were 2 or 3 points that he made. I think Doug and Chris, you'll probably have, and Neil, you'll probably have better context for this than I do. I've certainly looked at the mining numbers for rocks, for aggregate and sand, and limestone. They're just the biggest things we mine globally. When the gentleman whose name is, I'm terrible with names, so my apologies. When Brent was speaking, and I did review the Brent Constans podcast yesterday, Meta. When he was speaking, he made 3 or 4 claims which I felt were potentially a bit out over his skis, and he understated a couple of other things, is the way I would describe it. So the claims that he made about being out over his skis, I would say that saying that we're short of rock and sand when we're in a huge ball of rock floating in space is an interesting claim. I'd say there are local shortages and challenges, especially in his target space in San Francisco, where there's strong environmental requirements and a lack of ability to create new quarries. But I would not assert that we're short of aggregate in that regard. We are short of high quality sand for beach remediation and for other uses. That's an interesting point, and I'd like Doug and others to comment on that. But the point that I was interested in, he is correct in terms of the his comments around carbon capture and creation of CO2. I've dealt with Graciela Chichelniski and Peter Eisenberger of Global Thermostat. I've had David Keith tell me I was quite a horrible person to my face over a Zoom call based upon my comments, my entire case study on carbon engineering, which is a complete and utter waste of time and money. The assertion that Constance made about the energy requirements of carbon capture are bang on. The most expensive part is baking the CO2 out of the carbonates that it's being captured in. And so as he articulates the continuous filtered solution for flue carbon capture, and then taking those aggregates or taking those carbonates and turning them then into a solidified aggregate, that actually is a lower energy requirement. But he is very silent on the actual costs. He never mentions the cost variance between those things. And so as I look at the San Francisco Terminal 1 airport, I believe it was that he mentioned, that's a specific pocket of the future where they'll pay through the nose for carbon neutral and carbon negative cement. And so the question I have is, I'm going to say this really clearly, sand and rock is dirt cheap. And so his materials are not dirt cheap. And I don't know, he's apparently got a very fast mechanism there, but I don't know what the price point is. So Doug, Neil, Chris, others, comments on the aggregate argument that he makes in terms of the economics and availability, please.
Good question on the economics. I think that's the main concern here. Can he scale it up, and at what cost? Even cement, it's about 7 cents a pound, or 15 cents a kilogram. So if you're going to replace something that costs even carbon capture, you're looking at 3 to 4 times increase in cost. And some of the so-called carbon negative things, and I can't speak to Blue Planet specifically, would push costs by a factor of 10 or 20. The claims of carbon negative materials. So I think it's a tall order. Can he scale it up, and can he do it economically? You're right about San Francisco. Like you say, they're going to pay any price because it's a cachet thing. But run-of-the-mill residential construction with low strength concrete, you'd be making things out of wood pretty soon.
The thing that bothered me was the access to the calcium, because his technology depends on using demolished concrete. And I imagine you're going to use that up in 2 or 3 years. And then where will you get the next batch of calcium? And if you're going to get it from going back to limestone, then there's obviously no percentage. And as far as I can tell, I can't see how you've made any progress that way. So I don't know, what's the next best source of calcium after you used up your demolished concrete?
Good question.
I'll start.
Oh, go ahead, Mike.
I'll just say the building stock globally is transforming fairly rapidly. Buildings don't last as long as they used to. We are replacing, which is a problem. One of the simplest things we can do is not tear down old buildings and retrofit them. And so at least in the developed countries, there's a greater trend towards that, refurbishment. And then the embodied carbon is just sitting there still, and we don't care. We just insulate, electrify, and we've got a low carbon building from that perspective. But having lived in Singapore for 2 years and traveled in Asia, I know that things massive concrete structures disappear and reappear in very different forms in exactly the same space very rapidly. So as we articulate the potential for concrete waste, there's a lot more than you might think, Meta. As an example, while the new city council in Vancouver is putting this under reconsideration, we're talking about getting rid of the Georgia Viaduct here, which is a massive concrete span of bridge with an awful lot of concrete in it. Now the question there is, how much of that, as he grinds it up, and what is the energy required for grinding it up and purifying and getting rid of the rebar and other components? That's other questions around, the Blue Planet technology. The question there is, what jurisdictions is cement a ongoing stream that is suitable for this, and what scale is it at? And it varies by country. It varies by other things. So.
Just coming back to the economics, this is Chris here. There's also the fact that they are sequestering CO2, and I thought there was a payment for sequestering CO2. That there's a price. There's a price for that sequestration that maybe changes the economics of that process.
When I listened to him, his articulation was pretty clear that it needed a carbon price, but it also needed the tip price. Basically, he's diverting waste from landfill, where you have to pay per ton for landfill, and that's a saving. And then you've also got the carbon pricing. As we look around the world, carbon pricing is pretty iffy. The carbon border adjustment, which included domestic manufacturing and industrial carbon pricing in the United States, was axed by Manchin earlier this year. So that one is in abeyance. The EU's ETS and carbon border adjustments are increasing, which is good. China, to mention China again, has a new carbon market, which is twice the fiscal value of all of Europe's at the present and growing. And we, of course, in Canada are getting the excellent carbon price, which is increasing through 2030 at present to almost enough. Like 133 US is about $50 short of where it needs to be. So watch that space. If rational economics prevails, it'll go up again. That cap of 170 Canadian will be removed, which would be good. So yes, that is kind of the question mark there. To another point that Doug made, though, a significant number of there's two fossil fuels commonly used that Doug was talking about: powdered coal and natural gas. Inside that clinker thing where the quicklime is mixed with clay, there's a jet of flame that's 5 meters wide and 10 meters long. It's just this absurd jet of flame. That is powdered coal or natural gas. Coal, we've now been discovering, methane emissions from coal beds are much more significant than we expected. And upstream methane leakage from natural gas has turned out to be a much greater problem than was expected as well, with an average of 1.5% global upstream fugitive emissions. For context, that means that natural gas electrical generation is 200 to 330 grams of CO2 per kilowatt hour more than we thought. It's supposed to be 400 to 450 just for the CO2. It's actually 600 to 750 grams CO2e per kilowatt hour, which is in the range of really good coal, by the way. So that's kind of the point, is we're going to start seeing CO2e emissions being priced and managed, which will also impact cement manufacturing, in my opinion. And so that'll drive, if we do this intelligently and carefully and slowly, that will drive electrification and refueling and a bunch of other stuff. But it's a hard target. Cement manufacturing, as Doug's pointed out, is the biggest thing we do.
The technology to electrify the kiln operation of cement plant, they're working on it, but it's not there yet. They've tried hydrogen fuel recently in the UK. There was a trial of hydrogen fuel firing of the kiln, but it's a lot more difficult because it's not like the electric reduction furnaces where they're using big carbon electrodes and melting the material. We can't melt the cement. It's got to remain, it's like a ceramic process. And so it's a lot more difficult to control that. And the long residence time in that big flame is to get these reactions to go through to completion, so that the cement does what it's supposed to do. So they're working on it, but I think we're a long way off from electrified kilns, unfortunately. other things in the process, like turning the mills, like the grinding energy is about 10 or 15%. That's electric energy, if it's clean energy. The trucks they use can be electrified. There's a whole bunch of things that can be done, but the kiln itself is difficult at this point in time. I'd say we're some time off from getting that in place. The cost of a cement plant, a single kiln cement plant, you're looking at almost $500 million for a cement plant. So if you say we're going to switch to electric plant, unless you can reuse the equipment that's there with those changes, it's a huge capital investment. And that's one of the things that prevents us from the industry, not us, the industry from turning on a dime with some changes. Even relatively modest changes are highly capital cost intensive. But anyway, that shouldn't stop us from moving forward.
Robin and then Adele, please.
So the first question is a basic question, which I probably should know the answer of, but I'm coming late into this conversation. My assumption is that existing buildings that have been built with cement do not continue to produce CO2, but that the CO2 production is in the burning off of in the limestone process.
Mhm.
Is that generally the case?
Yes.
Okay. So when we speak of carbon negative cement, I'm assuming that what that means is the buildings will continue to absorb carbon dioxide. If that's incorrect, please clarify. If it's correct, how is that done?
Well, it's funny. It's concrete will absorb CO2 into the surface. You get a carbonate reaction with the calcium hydroxide and the calcium silicate matrix, but it's slow. CO2 diffuses in, so it's a slow process. You'll see the outer 10 or 20 millimeters over many years carbonate. So it is sequestering CO2, but only a small fraction of what went into it, making it in the first place. If you crush it, if at the end of life, if you take down a building and you crush it into aggregate size and leave that in a stockpile for a sufficient period of time, it will absorb a lot more CO2 because you're exposing a lot more surface area to carbonate. You can carbonate most of what's there. Now, what percentage that is of the total, I don't know. So there are opportunities, but there is some sequestration over the lifetime, but I would say it's a small. I think you're looking at 5%. And some people are saying we should make concrete that carbonates better to sequester more CO2. But one of the things that causes corrosion of steel, rusting of steel, is when concrete carbonates, it loses its pH and then it makes the steel liable to corrosion in a moist environment. The big thing we worry about in Canada is often de-icer salts or sea salts to do that. But in a lot of parts of Europe and Africa and Australia, carbonation is what causes a lot of the deterioration because it also reduces the pH of the concrete and makes the steel, the reinforcing steel, susceptible to corrosion. So it's a funny thing. And of course, it's the outer part of the concrete that protects the steel. And that's the part you don't want to carbonate.
So this surface absorption, are you referring to all cement or are you talking about carbon negative cement?
All concrete.
All concrete.
If it's exposed directly,
Okay.
not painted over or something.
So the negative we're talking about has something to do with something else. Carbon negative concrete is not about this surface question. It's something else. What are we talking about when we're talking about carbon negative cement?
Well, why don't I take briefly the Blue Planet argument?
Okay.
What they do is they crush recycled cement, and they do run it through the carbonate process, drawing CO2 out of the atmosphere, and then they make aggregate from that calcite, and so then they rebind that into cement, and so what you have is an aggregate which is drawn partially out of CO2 from the atmosphere. But that is the process of making the aggregate, not after the aggregate is used with cement to make concrete.
Okay.
And that's one example of this type of thing.
All right. The other two questions directed, I guess, at Doug too. In one of your early graphs, you said that timber was the greater problem in terms of CO2 production. Can you clarify? It was by far the larger problem. This is after it's been cut and used as a construction material. It's still exuding carbon dioxide. Is that what you're saying?
No, I think, that graph was developed at Bath University and they talked about it. They had some qualifier on that. the wood industry says they're sequestering carbon. What they're doing is cutting down trees that did sequester carbon, using a fraction of that to hold that carbon in the wood structure. And the stuff that's left on the ground deteriorates over time. It might produce methane, which is 20 times worse than CO2. And so they're not using all of it. Now the industry's gotten more efficient at using the wood waste and, cross-laminated timber, all these various products they make now to produce less waste of their timber. But you're taking something that you're stopping the carbon sequestration when you take the tree down. And yes, you can replant the trees, and they claim that's neutral because they're replanting. But you're sequestering the CO2 not immediately, but over along many years and decades till those trees grow again. So I'm not sure how that plays into the numbers at Bath University. I don't know how they calculated those numbers. You'd have to talk to was it Hammond and Jones.
Okay.
At Bath.
And to be clear, those are, I would articulate that there are significant studies which say the opposite. This is a matter of some debate. A big part of the problem in a lot of these things is where you draw the system boundaries.
Sure, absolutely.
And the assumptions that you make around these things. A big part of what I try to figure out is where the heck is the system boundary being drawn? Because this doesn't make sense, right? Like if you look at a lot of stuff out of the fossil fuel industry, they're drawing it so tightly that they're ignoring enormous amounts of other things. And so this is a case where I personally haven't seen a meta-analysis or systemic review of all the literature that I consider credible across these spaces yet, but I also haven't gone looking heavily for one. So,
Okay, Doug, if I can, I'll get the source of that piece from you, so I can follow up on. Okay, and my final question was, you were saying, Doug, that the industry was targeting 50% reduction carbon problem by whatever 2030, something like that.
40%, I think, is the number that came up.
Okay. Given the scale of the problem, is that fast enough? And let's include China in this conversation. Let's include all concrete in this conversation.
Mm-hmm.
Is that fast enough, even if China were to do the same thing?
Well, it's a good question. Now, nothing is fast enough, I guess. But it's also about the ability for the industry to switch. It's not as simple as saying, as of today, you've got to do this. The construction industry is a very complicated industry. It's got many moving parts. You've got a lot of players. You've got owners, specifiers, designers. You've got contractors. You've got materials suppliers, cement to concrete, and aggregates to concrete suppliers. You've got contractors, subcontractors, and the various trades. And all of these people are, and then so they're all potential barriers to change because they all see risk in change. And because a lot of it is legal liability too. In the building code, if a building collapses, these people could go to jail. So they're worried about how change is going to affect the structural safety. No, but I think it's more than that. To me, that's more things fail out of durability problems. They deteriorate faster more often than they collapse from structural issues. So it's not a simple thing to move quick enough. But the other thing is the demand for concrete has to do with urbanization. Both India and China and the developing it, they want the same things we've got, and the population is growing. This whole thing is population driven, right? So as long as the world population grows and we move to urbanization, China's had a huge urbanization, gone from a rural country to an urban country very quickly. And I've been to China many times, and it's amazing what they've done, and their lifestyle has changed. But there's a cost associated with that, and they build these things, big infrastructure projects. I was on a freeway that was supposed to last 100 years, and it was less than 10 years old. It was already deteriorating. Not that their cement wasn't any good or their concrete wasn't any good, but a lot of their labor is very low level. And so things don't get executed always well. I'm not saying that across the board, but I've seen evidence of it where things that should have lasted 100 years are not going to last 20. And we see buildings coming down in China because they changed their minds about where things should go, or that recently, toppling multi-story buildings before they're even open. So it has to include the whole planet, I think.
My question is in the chat. It seems to me that
Right.
these issues would get a big boost if COP27 was talking about them, at least in some way, so that now the entire Asian and Western nations were on that topic. So is anything happening there?
Yes, actually, I just got an email today with a link to a report submitted to COP27. There is a cement like a bunch of academics, including Karen Scrivener from EPFL, at COP27. They've issued a report that was released today. At least I was able to get it.
Sure. And just in reply to Robin's question, is a 40% reduction by 2030 fast enough? I mean, that's roughly the target that the UN has said we need to stay below 1.5 degrees of warming, right? So the 45% by 2030, net zero by 2050. So I think that, is it fast enough? They're answering the question that the UN has posed anyway, at least as far as that industry is concerned.
The one thing the cement industry has said in the United States, though, is they want government CO2 taxes, because a lot of the things they want, because of the cost of putting some of these things in place, the capital cost, it'll be the CO2 taxes that drive them in that direction or accelerate their change. So the industry is asking for it. They're willing to move. They're asking for it, but they need that sort of carrot and stick approach with the carbon taxes.
Demographic, we've been dealing with global population growth, for longer and more seriously than we have been dealing with climate change. Grow Brundtland's Towards a Sustainable Future in 1982 said, make people affluent and, teach women family planning. That's actually working. The range of peak population is 27 to 2100, with 9.7 to 11 billion people. And so we are going to see diminishing population growth in the coming decades. So that rate of change is slowing, and we'll see peak population in the last quarter of this century sometime. So that's a beneficial thing. We're going to get out of the Malthusian trap with that regard. China's population is already fairly flat. They removed the one-child policy. The primary growth is in sub-Saharan Africa right now, which is a different problem space. But China, as another example, they've taken 850 million people out of abject poverty and subsistence farming and into the lower middle class and middle class, which has been, a tremendous advance, obviously. And, that does mean that, among other things, they aren't having nearly as many kids simply because of that process. And so the question is, those curves, I am optimistic about us achieving, at some point this century. We'll finally be out of that Malthusian cycle, but that's going to be what it is. So
Adele is waving her hand.
Okay, well, just rebuilding all the housing that's been destroyed in Ukraine requires one heck of a lot of concrete, and one would hope that it could be the better concrete.
Mm-hmm.
Just a comment.
Mm-hmm. Okay, I think we've used up our time and then some, but I want to remind you that when you go to the website to savetheworld.ca, I hope to have this up by sometime tonight, and it'll stay there indefinitely, and lots of people will come and look at it. And if you have another thought or another dispute that you want to pursue, there's a comment column below. So I want to encourage everybody to go check out that comment column and add any second thoughts that may occur to you or questions that we could address in subsequent shows, because we're going to be holding one of these shows every Monday about one or another of the 4 different issues that we're concerning, that the POCRESH group has decided to investigate over the next 4 months or so. So if you have another thought at any point during that 4-month period, or even later, come and add your thoughts on that comments column, and you can debate there. You can reply to each other and so on. And so that will give us an opportunity to pursue whatever unfinished business we may have here today. I want to thank you all It's been extremely useful, very valuable, and I think we can make a real contribution to public discourse by sharing this kind of show with our network, the people who need to be talking about such issues as climate and concrete. We can help stimulate a conversation, and that's really what's going to be putting the political pressure on all the decision makers to do the job as fast as we possibly can. So thank you all. And
Thank you for
Thank you.
inviting me.
fine.
Thank you.
Bye.
Very useful. Bye.
Project Save the World produces these shows, and this is episode 522. You can watch them or listen to them as audio podcasts on our website, tosavetheworld.ca. People share information there about 6 global issues, too. To find a particular talk show, enter its title or episode number in the search bar, or the name of one of the guest speakers. Project Save the World also produces a quarterly online publication, Peace Magazine. You can subscribe for $20 Canadian per year. Just go to pressreader.com on your browser, and in the search bar, enter the word peace. You'll see buttons to click to subscribe.